Hello everyone, my name is Heidi Fair and I'm going to present a project that I've done and I called it the Personalized Biomechanical Simulation of a Human Femur Bone. Personalized because this is my femur bone. So let's just get straight into it. Here's the agenda, everything I'm going to talk about, the motivation of why I did this project, how I made it, my meshes, my simulations, all that really good stuff. So motivation and background, and what is this project really? So more recently there's been a focus on what is called personalized medicine. So this is when you're using information, for example, you take a blood sample of someone and because of the way their blood is made up, you make a treatment plan especially for them. So instead of doing a blanket statement, because humans, we're all different, everyone's bodies is different, everything is different. So instead of having a blanket medication for everyone, we can actually look at how people's DNA is made up and we can make individualized treatment for them. So this also exists in biomechanics. So for example, custom implants, making a implant that fits perfectly within someone's leg or arm. We can also use personalized medicine to assess fracture risk for people. We can make personalized intraoperative decisions. I've heard of engineers finding ways to measure strain in ligaments. That way the surgeon can measure the strain in a ligament and then do a surgery and have it come out perfect. So in this project, I'm doing a femur bone. And I'm actually CADing and I'm simulating my own femur bone. And why did I choose this? So women, I'm a woman, are more likely to develop osteoporosis because of the geometry of our bone and also because of some hormonal things. 1 in 7 women will experience a hip fracture. And so saying hip fracture isn't exactly correct because the hip is a joint. A hip does not fracture. A hip is it's your ligaments, your muscles, everything together, the whole joint, that's your hip. So you don't really break your hip, same way you don't break your elbow, you break your bones, right? So anyways, that's why I'm doing a femur. That's why it's called a femur, not a hip. So as you can see here are some images of how femurs break hip fractures. And I know that as a woman, I'm at more risk of breaking my hip in the future, so I wanted to do this simulation just to see if that might happen or not. So a little bit of background is that FEA and simulations have been used for this before. All the way back in 1972, they've been using mathematical FEA to characterize skeletal parts and see all the mechanical behavior in bodies. And there's also been more recent FEA studies also using simulation software similar to ANSYS, which is what I use. And there are some papers on crack propagation in the femoral bone, simulation of a sideways fall, and all of these, as you see, there's citations. I'll put them in the description below, and there's also a final slide that has all of these points, all of these references. So as you see this little image, that's actually a screenshot from the paper that discusses the crack propagation in the femoral bone, and you can see how they did that. So what are the objectives of my project? So I'll read you the whole statement here. So to develop a pipeline to simulate, and therefore better understand, personalized reactions to bones on impact. When I say the word pipeline, I refer to I want to be able to make a model that can be replicated with different individuals and it can be rerun with different parameters or situations. The point of making a simulation is because it's non-invasive, which is great, and to understand, the green one, this type of work can inform the direction of future research. So one of the studies that I might mention later on, they were actually studying how to design a better kind of like a covering for the hip for elderly women to wear so that they don't have as many injuries. And these types of simulations can help give more insight into, what materials can they use for that? How can they do different, how does it react with different types of falls, that sort of thing. So a lot of this is to help just general understanding for future research and clinical studies. Personalized, of course, that's a big part of it. We can detect if people are at risk. And myself, I can detect if I'm at risk to break my hip. And I also highlighted the word bones because in this case I'm doing a femur, but you could do the same thing with, different muscles or different bones, your arms, your knee, everything, right? And then impact, this can also be used to advise athletes who do high impact maneuvers. This is just one of the applications that this type of study could have. I'm not applying it in this case, but you could potentially. So my objectives, so the things I need to accomplish to reach my goal, I'm doing 3 simulations. Sorry for the noise, I have a really cute cat who's kind of running around. This is YouTube, right? Cats. So the first one is a counter movement jump, and I performed the simulation to validate it. So I have experimental data of myself jumping on force plates, and I wanted to see if my simulation gave me something reasonable. If I jumped and it deformed, 2 meters, well, obviously, there's something wrong with my geometry or my material properties or something. So I did the counter movement jump because I have the experimental data, I know what everything should be, and I want to see if my simulation is sensible. After that, I used the same geometry to conduct a simulated fall on the same femur. And this is kind of just like to display a real-world application. And finally, I checked the effective age on the simulated fall. So I modified my femur as if I got older, just to see if maybe now I'm more at risk at breaking my hip. So geometry, I'll have to be honest, I think this is the part that took me the most time, and you'll see why. So I did not have access to a CT scan of my femur, but I was able to get x-rays. As you can see here, you can even see my name is on them. The technician was very helpful, and he provided me with some of the measurements, like the length of my femur, which is 47.3 centimeters almost, and some of the dimensions of the cross sections. Using this, I was able to use a software called ImageJ, which basically allows you to measure images with the scale. So with these images, I was able to find like the critical dimensions so that I could CAD my own femur. So again, I designed it from scratch using ANSYS Workbench. Because I did try importing some scans of other people. My first idea was I can import a scan and scale it to my dimensions. However, they were so complex, they had so many facets that I had a student version of ANSYS. So even every little tweak I was trying to make, it was crashing. It took 5 minutes to create one dimension. So it was not working. So I decided to go the more simple method, which was still work, right? I had CAD'd it from scratch. So here you can see it overlaid. It kind of follows, of course, there's some areas where it might not be perfect, but I tried to follow the shape and the dimensions as much as I could. This is what it looks like, and here in the next slide I will show you more. So here are some of the dimensions, just so you know. So the height is, just like my x-ray shows, 47.23 millimeters. Sorry, that should be centimeters. That's the only one I didn't do in millimeters. My bad. Maybe I'll correct that on YouTube. But yes, sorry, this one is centimeters. But the rest are all millimeters. So some critical points that I thought you might be interested in the dimensions of is here, the femoral neck. It's the thinnest part of my femur. Also here, the cavity, because femurs are filled with bone marrow. So I emptied it out, and then the cross-section at the smallest point is 14.63 millimeters. And then these are the diameters of the loft I made for the shank. So D, E, and F. Here are some close-ups of the femoral head and femoral neck and the greater trochanter. I'll admit the trochanter does not look exactly how a trochanter should look. That's this part. But it was a complex thing to design, and that is what I ended up with. So I think for our simulations, it's sufficient. Mesh optimization. So once I was able to have the 3D model that I made, meshing was a lot easier than using the scans. mesh optimization. So first, I just did, the general default mesh and saw where do I have bad element quality. So obviously here at the top where there's like the weird features, and at the bottom. So here we go. This is where we see the kind of the bad parts. So because of this, I decided to simplify it a little farther, and I cut off the bottom of the femur because this wasn't really helping us, right? We're going to have our supports near the bottom, and we're really interested in what happens in the neck and the head over here. So I just cut that off to at least eliminate some of the elements and clean it up a little bit. So I did a convergence study, and as you can see with displacement, it seems to converge around here. And for equivalent stress, I think it was converging. However, I could not generate any more nodes because since I again have the student version of ANSYS, that was kind of my limit. So I selected this point, which was 6 millimeters, because it gave a little bit better skewness than the smaller one. So this was my selected parameter. So here we go. Here's the description of it. So the mesh element was 6 millimeters. I used the hex dominant quad/tri. I saw a paper where they did the mesh of a femur, and they both had their good sides and their bad side using triangular meshes or quadrilateral meshes. So I decided to go with the quadrilateral, well, the hex dominant, which uses a little bit of both. Here are the amount of nodes and elements I have. The skewness was 0.99, which is really bad. You usually don't want to have anything more than 0.95, but no matter how much I tweaked the model, I just really couldn't improve that. So it is what it is. I think it serves our purposes still, even though it's not a perfect mesh. Mesh quality average is 0.57817. Here's some more shots. So we can see, where the model is solid, it's not very nice. Here's a close-up of the femoral head and the femoral neck and the trochanter area. Here's also a cross-section of it. Again, these are not very good meshes, unfortunately. So boundary conditions. So the most important part when it comes to bones, and maybe the trickier part to nail down, is the material properties, because bones are very, very complex. They're very complex composites. They change with age. They differ from person to person. If you're male or you're female, your ethnicity, all of that can impact your bones and how they're built up. And as you can see in this image, you have the cortical bone, which my whole model is cortical bone. But in reality, inside the femoral head and the shaft, you have the spongy bone and then bone marrow and cartilage, and it's very, very complex. So I simplified it for these purposes due to time constraints. It is what it is, right? So here are the properties I used. I used the bone density. I got it from a study where it had a table of different genders, sexes, ethnicities, and ages. So I selected the white female, age 20 to 29. This was the median density. So that's what I used. The longitudinal and transverse modulus I got from a paper, and that's just an average of all bones. This isn't like specific to my age or to my sex, but this seems to be like the most reliable number I could find. The elasticity modulus, some papers will report anything from like 1 gigapascal to like 30. There's a huge range. I looked through a lot of different literature, a lot of different reports, and they were all kind of, it's not that clear. It's not that clear cut because the way that you test the bone in a lab can differ a lot. So also from the same paper where I got the modulus, the modulus of elasticity, those are some of the ultimate strengths of cortical bone. So for the first project, or for the first part, which is just the jump, I used, like I said, experimental data. Oops, I did not know it had volume. And so there you see me. That's me. I'm stepping onto some force plates, and I will perform a counter movement jump, which is just when you bend your knees and then you lift off. And on the right here, you see a graph, and I plotted absolute angle of the femur, which is this. You can see airborne, landing, how it tilts, and then it stands back up straight. So 0 would be standing straight. So the peak force on the force plates is up here, which is 1,950 newtons. And that happened when the femur was at 29 degrees. This is like the reference point, right? The video is kind of flipped around. So this is the value that I used. I figured this is the most important. It's the peak. And again, we have to remember that this number is a landing of the whole body, both legs. So for the studies, I divided this by 2. So this is where I got the impact, like the force at the jump. Here are the more of the boundary conditions for the counter movement jump. Here's a free body diagram of a femoral head, and you see that you have the force of the joint, the weight, and a muscle is also acting. So in my case, at the bottom I put the support, so I wanted to see what's happening up at the top. And we have here the landing. This is the landing, right? So this is 975, which is half of the experimental data. And it's in different components due to the 29-degree angle. And then we have the muscle, which according to one of the papers I read is about 52 degrees. And you can estimate it by doing 1.72 times your body weight, which in my case is 915 newtons. So these are my boundary conditions, my forces, my supports for the counter movement jump. Now for the fall, you see that the femur is horizontal, and I have 2 fixed points. I have the bottom of the shank, as well as the femoral head, which has a frictionless support. For me, this is like simulating the fact that there's a body on top of it, there's a body up here. It's not going to let that femoral head move. That's, in the pelvis. And then we have the force of the fall, which this is the direction of it. And then, no, sorry, this is the force of the muscle. This is the force of the muscle, also at the same angle, 52 degrees. And then this is the force of the fall, right? It's just vertical. And I got the value of the fall also from a paper where the moderate fall impact is considered to be 2 times body weight. So that's what I did there. And in that same paper, they said that the forces produced by the muscles in this scenario is around 80 newtons. So I went ahead and simulated that. My third simulation is aging, the effect of aging on fall. So I set up the model the same, as you can see here, the exact same as the previous slide. But what changed is the elastic modulus of the bone and the density. So this is based on the paper I previously mentioned that had a chart of all the different ages and their density. So I found out that around 80, someone like me, I would have a density of about 500 kilograms per meter cubed in my bone. And here is the relationship between elastic modulus and density. There are a lot of papers that say, yes, elastic modulus is related to density. This is true. Not that many that actually report, or at least that I was able to find that report the relationship. I was able to find this paper, which gives me a really nice, formula, so I could plug in my density and see what the elastic modulus is. So in this, according to this model, the elastic modulus in my femur right now would be 3.2 gigapascals. Previously, using the average, it was like 17. So that's really, really different. And then when I'm 80 plus, it would be about 5 gigapascals. So again, like I said, elastic modulus, there's a huge range of studies. So I did this one independently. And then here at the bottom, we can see just the little relationship, right? Age, the older you are, the lower your bone density is, and the lower your elastic modulus is, which is why it's more common to break your hip the older you are. So now let's get into the actual simulations and what the results were, and we can discuss, or I'll discuss to you. Okay, right, so the jump simulations, the counter movement jump, I studied the total deformation and the equivalent stress. And this was mainly, this was the validation, correct? So the deformation was to see if, did it make sense? I may have mentioned, but I had some simulations when I was tweaking things where my femur was deflecting 40 centimeters, and I was like, that's probably not true that when I jump, my femur is bending, 50 centimeters, curving, Okay, so, and then also the equivalent stress, I wanted to make sure that it's less than the known ultimate strength because, again, to validate, are the numbers we're getting making sense with the geometry and the material properties of the bone. So here's the total deformation. It's pretty small. The maximum deformation is 2 millimeters, which is reasonable. You might be surprised at how much your bones actually deflect just by moving around. We wouldn't really want rigid bones, right? Because then you would jump and they would all just crumble and crash. So 2 millimeters, that's reasonable. Here are the stresses. One thing to note is that, whoa, sorry about that. It's my desktop. One thing to note here, you can see all the different colors, which means that our mesh is pretty good in this area. Let's play this video. And here is the equivalent stress. And yeah, the maximum stress was 11 megapascals, which is, less than the ultimate compressive strength. So pretty good. I'm not simulating that my femur is breaking just by jumping. Again, oh yeah, here is the whole table in case you want to see it for reference. So the simulated fall, also total deformation doesn't make sense. Equivalent stress, if and where are the maximum stresses? If I were to fall, where would my femur break? And then finally the deformation by age. Here we go. Here we can see the total deformation. Now, oops. Is this one running? So this true scale one, it's actually hard to see because, there we go. It moves very little. It moves very, very little. And so I scaled it here so you could kind of see like in what direction would it be moving. So very, very small deflection with the fall. And that could be because I'm lightweight, maybe I have a really young, strong bone. There's not much of an issue with the deformation if I were to fall horizontally. Okay, equivalent stress. Where are the stresses? This is important. The stress is bigger than in the stress found in the jump, where it was like 11, and here it's 15. So there's more stress on the femur in this position. And we can see, as anticipated, that a lot of the stress is here in the femoral neck, right? These are where the fractures usually occur. Here is where the maximum stress is. It's kind of hard to see, and it's sorry, I lost my train of thought. This could, okay, so the maximum stress here, it could be due to the geometry. It's a really sharp edge. It's not really a great design. It's not organic like a real femur would be. But we can see that some of the breaks actually occur in this region. So that's possible, enterotrochanteric fracture. But then there's also a lot of stress here, which would be kind of like in the middle of the neck. Again, for your reference, here's the ultimate strengths. Tension, right? So here we would have compression, here we would have tension, or opposite. Here we'd have compression, here we'd have tension. But either way, it's still not breaking, which is nice. And then here's a total deformation with the different ages, with the new Young's modulus. The stress wouldn't change, right? Because the stress, we're just looking at the force and the geometry. But the deflection does change from 0.2 millimeters to 1.44 millimeters. So that is a difference. Right? Okay. Here we go. Conclusions. Here's my statement. Again, so did I actually accomplish what I went out to? So I wanted to develop a pipeline. So yeah, I did. I created a model and I could be set up to run many other simulations. For example, I attempted to simulate what, if I just dropped the femur on some concrete. Got some big stresses going on, 50 megapascals. It took a really long time to run and it was kind of complicated. I had a lot of tweaking to do. Did not have time to correct it. But this is one of the things that could be done. I also attempted some 2D simulations, which are the ones I mentioned earlier, that's some crazy deflecting. That is true scale. so you can see. And now I do feel like I do understand my femur better, and now I have a better understanding of my future risk. If I were to be able to get, better material properties, maybe I could even see a fracture. And, that's just good to be aware of. Even calculating, there's studies of, are you more likely to break your hip if you land with your hands on the floor, if you fall to your knees first and then go over to the side, you go to the front. So these kind of things, even for your own fun, you could model them, and you could, make a mental note like, okay, wow, if I fall, I should probably, try to direct myself. You can't obviously always do that, but anyways, I do have a better understanding of my femur and how it could fracture, and I was able to have a personalized model. So future work, there's so many ways that future work, more things that could be done with this type of project. You can account for the tissue and then have better muscular force. You could actually put muscular tissue and use the forces like that, because there's actually muscles all along the femur, right? Pulling it up all along the side. So you can account for those types of things. Also, your tissue is going to add a little padding to your fall. You can recreate it with better material properties. Maybe do more of a study. To be honest, I did not write down every single reported value of Young's modulus in a femur and then do a study on it. But you could. Also treating it as a composite, has different transverse and longitudinal strength. So you could do that. You could add, the sponginess inside of the femoral head and the femoral neck. You could obtain CT scan data if you have, faster software than I do. Use the geometry, and then from the CT scan, you can also get better material properties for yourself. And then, of course, there's so many more simulations. You can do dynamic simulations, fatigue, etc., etc., etc. So there's a lot of work to be done, but I think this was a really good launching pad and just setup of a clear initial pipeline where you could take off and do a lot more simulations if you wanted, and it's been validated, it makes sense, and that was what I was mainly going for. So here are my references again. They'll be down in the description, because I think it's pretty important in case you're curious about any of the papers I mentioned or where I got my values from. And here's a picture of me, and that is my contact info in case you have any comments. Again, I'm open to comments or maybe ways I can improve my simulations or questions. You can leave me a comment below, or you could contact me at that email. So thank you for your time, and thank you for listening, and have a great day. I hope you enjoyed this video.